Every time you use Google Maps or connect your phone to GPS, you rely on the physics of time moving differently at high speeds and higher altitudes. Those engineering corrections show how relativity affects our daily lives, but Einstein's equations go even further, predicting that along the path of light itself, the passage of time becomes zero. That raises a profound question. Could time truly vanish at the speed of light? In 2025, new research is sharpening this mystery. JILA physicists measured time dilation across a single millimeter with cutting-edge atomic clocks, while particle collisions at CERN revealed updated entanglement effects near light speed. These advances push Einstein's puzzle to the smallest and fastest scales we can observe. So why does something as ordinary as time begin to behave so strangely when speed increases? The strange relationship between time and light. At the center of this discussion lies the strange connection between light, motion, and time itself. Ordinary experience anchors us to the idea of time moving steadily forward, yet the rules of physics show something very different once light enters the picture. At speeds approaching light, seconds no longer align, and clocks disagree on how much time has passed. For light itself, the one thing in the universe that always moves at this maximum speed, the mathematics of relativity indicates that time, as normally defined, has no role at all. This insight arose in 1905, when Albert Einstein's theory of special relativity overturned the assumption that space and time exist as separate, universal backgrounds. Instead, they form a single geometric fabric known as spacetime, where an object's path through space must always balance with its passage through time. Moving faster through space reduces movement through time, meaning that one cannot accelerate without consequence. At low speeds, this imbalance is undetectable, but as speeds climb toward light itself, the changes become too large to ignore. One simple way to picture the effect is with two identical clocks. Leave one on a desk at home, while the other joins a spacecraft accelerating close to light speed. When both are later compared, the traveling clock will mark fewer ticks. This thought experiment has real-world confirmation. In the 1970s, aircraft carrying atomic clocks returned measurably out of sync with those that stayed grounded. Modern experiments have sharpened these results far beyond aviation. In 2014, particle accelerators timed lithium ions moving at tens of thousands of kilometers per second, confirming that their internal clocks slowed exactly as relativity predicted. In 2022, JILA researchers showed measurable time dilation across just 1 millimeter, using optical lattice clocks sensitive enough to detect gravity's pull at that scale. Together, these experiments anchor relativity as a tested and practical description of how time shifts under both speed and gravity. Imagine now what happens as motion approaches the cosmic speed limit. For people in a near-light-speed ship, biological rhythms, heartbeat, breathing, and even cellular activity would all slow relative to those left behind. The passengers would feel unchanged, but once reunited with others, they would discover that far more time had elapsed in the outside world. That is time dilation made real, a consequence of being massive objects moving close to light speed. However, the laws of physics impose a hard boundary. As velocity climbs, the energy required for further acceleration grows without limit. For this reason alone, massive things, humans, spacecraft, or even single atoms, cannot ever reach the exact speed of light. This brings us to photons, the carriers of light. Unlike anything with mass, these particles always move through the vacuum at precisely light speed, with no need for acceleration. Here, relativity gives a striking mathematical result. Along a photon's path, the quantity called proper time is zero. Put another way, special relativity does not allow a valid inertial rest frame for light itself. Physicists sometimes say that light experiences no time, but this is shorthand for the rigorous idea that a photon's world line stretches across space without any interval in its own proper time. To outside observers, A photon might travel for billions of years across the cosmos. Within the framework of relativity, however, no duration attaches to that journey. This distinction is important because it marks the edge of what the theory can describe. Humans can approach light speed in thought, but cannot attain it in practice. Spaceships and astronauts have rest mass, and so remain fully subject to time. The notion of time stopping at light speed is therefore only a mathematical expression, not a physical state available to us. When said carefully, it refers to the way special relativity compresses proper time to zero for any worldline at exactly light speed. Confusion arises when this phrasing is taken too literally. Still, the implications are profound. If light has no internal clock ticking from one end of its journey to the other, then time may not be a universal stage set on which events unfold. Instead, it is a relative measure that depends deeply on the properties of the traveler. Relativity already showed us that motion through space alters time's passage. Now photons highlight the extreme possibility, a condition in which the familiar rhythm of time does not appear at all. This contrast tells us something fundamental about the difference between things that possess mass and those that do not. None of this is speculative. Around us, technologies must constantly adapt to these relativistic rules. Satellites orbiting Earth require adjustments to keep their time systems aligned with ground clocks. Particle accelerators confirm relativistic effects every time high-speed ions decay more slowly than expected. Light from distant stars provides both a clock and a mystery, arriving billions of years after departure while still carrying no interval of proper time along the way. Everyday tools and cosmic signals alike are grounded in this strange relationship between light and time. For physicists, the lesson is clear. The closer something comes to light speed, the more severely its perspective on time diverges from that of slower observers. For light itself, the measure of time collapses into mathematics without human analogy. And for us, bound by mass and energy, the speed of light is a limit we cannot cross, but one that defines every constant of the physical world. The full significance of this becomes far more tangible when we look at technology that depends on these effects to work correctly. Only then do the abstract predictions of relativity reveal themselves in ways that touch everyday life, from navigation to global communication. When time runs differently, GPS is proof. Every time someone checks a phone for directions or watches a car's navigation system trace out a route, they are quietly relying on a reminder that time does not tick at the same pace everywhere. The global positioning system feels straightforward. Signals broadcast from orbiting satellites, receivers compare them, and a precise location appears. But what holds the system together is not just radio transmission. It is the alignment of clocks that mark time differently depending on whether they sit deep within Earth's gravity or speed overhead in space. Without those corrections, the GPS network would unravel in hours. The satellites orbit Earth at nearly 4 kilometers per second. That motion produces a special relativity effect, where moving clocks tick slower than stationary ones, reducing satellite time by about 7 microseconds for every day in orbit. But something else also acts, the gravitational effect described in general relativity. Higher above Earth's surface, gravity's pull is weaker, and in this environment clocks run faster, adding about 45 microseconds per day. The two influences pull in opposite directions, and when combined, they do not cancel. Together, they leave the satellite clocks running about 38 microseconds ahead of those on Earth's surface each day. 38 millionths of a second may sound negligible, but GPS must achieve accuracy within a few nanoseconds. A mismatch that large would shift measured positions by kilometers daily. Within a week, the errors would grow into tens of kilometers, turning every phone and aircraft display into a misleading guide. Navigation systems, shipping routes, and air traffic would all be degraded. In that sense, relativity is not a side detail, it is a requirement. The time corrections needed to counter these relativistic effects are what keep our maps aligned with reality. Engineers solved this challenge with careful design. Before launch, each satellite's onboard atomic clock is tuned with a frequency offset so that once in orbit, ticking proceeds in harmony with identical standards on the ground. This factory offset corrects the net plus 38 microseconds per day discrepancy that relativity guarantees, but further complications remain. Orbits are not perfect circles, so speed and altitude vary slightly. As satellites pass through different parts of their orbits, their clocks drift by tens of nanoseconds. To prevent this fluctuation from accumulating into further distance errors, the network applies real-time corrections calculated on Earth and uploaded to the satellites. Through these adjustments, the constellation of more than 30 satellites stays synchronized, and receivers can exploit overlapping signals to calculate positions within a few meters. The reliance on this synchronization demonstrates how directly physics becomes part of engineering. Each positioning fix requires that signals traveling at the speed of light be timed against one another at the scale of billionths of a second. A single nanosecond error corresponds to a path difference of about 30 centimeters. By working at such precision, engineers cannot ignore effects that seem insignificant in most contexts. 7 microseconds lost from motion and 45 microseconds gained from weaker gravity add up to thousands of nanoseconds, and that in turn would cause vast displacements on Earth's surface. The technology works only because it constantly applies relativistic corrections. If those corrections were ignored, the consequences would appear quickly. Imagine disabling the relativity settings for a day. Clocks in orbit would accumulate tens of microseconds of offset. GPS receivers would interpret signals as arriving too early, and the mismatch would shift ground positions. At first, a person following turn-by-turn directions might notice instructions pointing slightly ahead of the car's true location. After hours, deviations would build into hundreds of meters. After a full day, navigational errors could measure 10 kilometers or more. For aircraft, this would mean straying off established airways. For ocean vessels, routes plotted from GPS alone would drift far from intended paths. Everyday transportation, finance networks depending on time stamps, agriculture, and surveying would fail to function with precision. The degree of urgency that relativity forces on GPS can be seen by comparing these numbers to the demands of accuracy. A 10 nanosecond time error is already enough to shift calculated positions by 3 meters. Engineers need atomic clocks versatile enough to maintain stability to within a few billionths of a second per day. Any greater drift would break the network's coherence. That is why GPS became one of the most prominent real-world systems to embody Einstein's predictions. No clock in orbit can be built without planning for how gravity and velocity stretch or compress the measurement of seconds. This feature of GPS also explains why the system works equally well across the globe. Engineers must compensate not only for orbital effects, but also for Earth's own shape and motion. At different locations on Earth's surface, gravitational potential and speed from rotation vary. Yet the combined effects conspire in such a way that time on the surface synchronizes uniformly, while in orbit the effects diverge and must be corrected. That design is what allows position fixes to appear stable whether in a city street, at sea, or on an aircraft crossing continents. The contrast is striking. In laboratories, physicists use atomic clocks to study relativistic time shifts across heights of a few centimeters. In orbit, satellites carry clocks that demonstrate those same principles on a global scale, every moment of every day. These orbiting instruments are not just transmitting coordinates. They are part of a continuous experiment verifying relativity's prediction that speed and gravity alter the pace of time. Every successful map pin and every accurate landing is evidence that Einstein's theory is part of the infrastructure of modern life. This integration has another effect. It changes how physics is perceived beyond laboratories. Relativity is not optional background knowledge for specialists. It is a silent requirement embedded into the electronics that billions of people use daily. Instead of serving only as an intellectual model of the universe, the theory directly stabilizes applications no society would choose to risk losing. That necessity underlines the point. Relativity is woven into devices we take for granted, and our trust in global positioning remains possible only because engineers treat its predictions as mandatory. Each corrected signal from a GPS satellite thus confirms something extraordinary. Time does not advance uniformly, and technological achievements depend on acknowledging that. Every flight guided, shipment tracked, or phone query answered owes its reliability to the fact that clocks diverge in orbit from clocks on Earth, and that divergence is reconciled by relativity. And yet, correction of these orbital clocks is only one part of physics confronting the fact that time flows differently under different conditions. The same question arises in another direction. What happens when we try to accelerate matter itself to ever higher speeds, reaching closer and closer to the ultimate limit at which light travels, pushing matter toward light speed? Our closest window into what happens as matter nears the ultimate speed limit comes from machines built to push particles with almost unimaginable force. These are particle accelerators, vast structures that use magnetic fields and electric gradients to guide charged fragments of matter until their motion nearly matches that of light itself. Instead of trying to hurl entire vehicles or people, researchers focus on the smallest building blocks, protons, electrons, and heavier nuclei, because they can be driven to extraordinary velocities under controlled conditions. Watching how these particles behave reveals the practical limits of relativity in action. The most powerful of these instruments is the Large Hadron Collider beneath the border of France and Switzerland. Stretching over a 27-kilometer underground loop, it was engineered to sustain beams of protons at energies so high that everyday intuition ceases to be a useful guide. By the time protons are circulating in its magnetic field system, they race at about 0.9999999 times the speed of light. At such speeds, their Lorentz factor, a measure of how relativistic effects grow, soars into the thousands. This makes the LHC the closest laboratory analog we have to an environment where matter brushes against light's ultimate pace, and why its experiments provide the clearest demonstrations of relativity under stress. What sets these conditions apart is not that the particles keep gaining velocity in the usual sense, but that most of the added energy is diverted elsewhere. Special relativity dictates that, as the velocity of a massive particle inches toward light speed, the required energy to continue accelerating it rises out of proportion. This additional energy does not make the protons move noticeably faster, since their speed is already within a whisper of the limit. Instead, the energy swells the particle's relativistic mass and dramatically alters the way time flows when viewed from an outside reference frame. If a proton could carry a clock, that clock would appear to outsiders as ticking more slowly with each incremental rise in energy. This reality is made visible with particles whose natural lives are fleeting. Muons, heavy cousins of the electron, normally decay in only about 2/millionths of a second when left at rest. Yet when these muons are produced inside accelerators at nearly light speed, laboratory detectors record them surviving for thousands of times longer than their stationary lifetime. The effect is not that the particle becomes more stable, but that time itself is stretched relative to our perspective. The muon still experiences its same proper 2 microseconds, but because of time dilation in the laboratory frame, it travels much farther before disappearing. The fact that detectors can measure this extension with precision makes muons a direct and highly persuasive confirmation of Einstein's predictions. Similar demonstrations appear naturally in the atmosphere. High-energy cosmic rays colliding with molecules overhead generate showers of muons that rain downward. By all calculations, their normal 2 microsecond lifetime should allow them to travel only a few hundred meters before decaying. Yet countless muons are measured at the Earth's surface, having survived journeys of tens of kilometers through the air. Their improbable arrival makes sense only if time dilation has extended their observed lifetimes, a phenomenon independently verified under controlled conditions inside accelerators worldwide. These parallel cases, one in laboratory rings and the other high in the atmosphere, reinforce each other. Relativity predicts the dilation, and nature confirms it. The reach of accelerators extends far beyond verifying lifetime extensions. Their collisions break apart protons into showers of more elementary particles, producing conditions that last existed only fractions of a second after the Big Bang. The discovery of the Higgs boson in 2012 was one of the defining achievements of the LHC, but ongoing runs continue to uncover subtleties in particle interactions. In 2024, the ATLAS experiment recorded evidence of quantum entanglement between quarks at unprecedented energy, underscoring how strange and interconnected the quantum world becomes at relativistic extremes. Yet behind these landmark announcements lies the same foundation. All of it is possible only because accelerators reliably push matter into the near-light speed regime, where relativity dictates the rules. It is important to note that none of this implies we can directly scale these results up to the everyday scale of ships or humans. Accelerators succeed because they manipulate subatomic particles with vanishingly small mass, using field gradients and superconducting magnets capable of forcing them onto near-light trajectories. The method works because the particles themselves are tiny and carry charge, making them responsive to electromagnetic control. No known engineering approach could replicate this on macroscopic objects like spacecraft, which involve incomparably greater rest mass and different physical constraints. The experiments teach us what happens to matter under those conditions, but they do not offer a blueprint for human travel at such speeds. The inescapable obstacle remains the structure of relativity itself. Each increment toward light speed requires more and more energy, with the demand climbing so steeply that it approaches infinity before the limit is ever reached. The LHC's colossal energy input and the billions of dollars invested in its infrastructure are required just to elevate tiny groups of protons to conditions that remain infinitesimally short of light speed. This escalating cost signals why nothing bulkier can ever achieve the same threshold. Calling it a barrier is not a figure of speech. It reflects a mathematical limit built into the geometry of spacetime. Over the past 2 decades, advances in accelerator design have pushed data quality to the level where relativistic predictions are confirmed to astonishing precision. Each measurement of lifetime extension, each observation of decay signatures shifted far from their rest frame expectations, strengthens the conclusion that the laws Einstein laid down survive under the harshest conceivable tests. Sophisticated detectors record billions of collisions, while teams refine equations to within microfractions of a percent. Far from remaining abstract 20th century ideas, relativity's principles are demonstrated daily in sprawling facilities that bring them to life through beams of particles moving at 99.999999% of light speed. Even so, what strikes researchers most is how sharply the curve bends as particles press ever closer to the limit. At modest fractions of light speed, the dilation of time is slight, hardly noticeable. But push into the realm of 0.999999999 C, and the effect grows monumental, inflating particle lifetimes and stretching intervals beyond everyday comprehension. This runaway escalation shows why attempts to imagine continuing the process to full light speed are not merely impractical, but ruled out by the theory itself. Our instruments therefore give us both a tool for discovery and a warning written into physics. Accelerators demonstrate vividly that relativity is real, measurable, and unavoidable. But they also emphasize that the same rules preventing infinite acceleration in a laboratory apply universally. Particles supply their own answer about the unattainability of light speed by showing us what happens as you try. Greater energy yields more dilation and more resistance, yet never the final goal. These lessons drawn from tiny particles prepare the ground for the question that naturally follows. If even the most elaborate machines on Earth fail to carry matter across that final threshold, what hope would there be for something larger? The impossible barrier of light speed. The barrier that defines the edge of possibility is the light speed limit itself. Special relativity makes clear that no object carrying mass can ever be accelerated fully to that velocity. The equations describe why. As velocity gets closer to the speed of light, the Lorentz factor, represented by the symbol gamma, climbs sharply. Because kinetic energy grows proportionally to gamma, each small increase in speed demands more energy than the one before. Near the limit, gamma trends toward infinity, which means the energy required also trends toward infinity. This mathematical rise is not just steep, it is unbounded, and that is why relativity describes light speed as an uncrossable threshold. The distinction between matter and light is central to understanding this boundary. Photons do not have rest mass, so they are not subject to the same acceleration rules. They simply exist in motion, always traveling at c, the constant speed of light in a vacuum. Matter, however, carries rest mass. Moving it faster requires supplying energy, and as velocity approaches c, that task becomes overwhelmingly difficult. At walking or even rocket speeds, burning chemical fuel is sufficient to overcome inertia. At fractions of c large enough to alter time perception, fuel demands no longer match what any propulsion method could produce. The conclusion from relativity is that no resource or engine can overcome this wall, because infinite energy does not exist in nature. A useful analogy is the act of sliding a heavy block. Once moving, it can be pushed along with manageable force. Imagine, though, that with every meter you shove it grows heavier. Eventually, the required force would surpass your strength entirely. That is how the resistance builds for any particle with mass. The mathematics says the increase never stops until the barrier is reached, yet that frontier can never be touched because the needed energy supply escapes all possible limits. Accelerator data confirm this relentlessly. The faster particles are driven, the more energy goes into sustaining barely perceptible gains in additional speed. It is the laboratory mirror of the same divergent curve that no technology can overcome. This barrier means matter and light occupy permanently distinct categories. Photons glide along at c, while everything with rest mass sits below. Any attempt to design spacecraft capable of equal speed collides with that fact. Every kilogram on board, whether hull, fuel, or cargo, would demand an unbounded energy supply to cross the final gap. Even the output of stellar furnaces scattered across galaxies could not add up to what is required. This is not a technological blockade, but a structural one, tied to the nature of spacetime itself. Time dilation, another prediction of relativity, reinforces the limit from a different angle. As speed increases, an onboard clock runs slower than the clocks left behind.